Alrighty then. Well, the thing has been hit. We're live. Hey guys, what's going on? Memes here, and I'm joined again by Echelon, our friend that's providing us with virtual physics. And today we're going to be exploring what you can do with virtual physics and how all the different little particles interact and everything. So, Echelon, what do you have for us? Want me to share the screen?
Yes, I have the screen up. Perfect.
All right.
Let me start when you download virtual physics, you're going to basically get these three directories. Applications is where the test code is, where I have demo code. You may have seen it in the README, and if you step through it, it's kind of using it, but it doesn't really. It just kind of shows superpowers, but it doesn't talk about what's going on behind the scenes. And so that's what I'm going to talk about here, how the particles work, how we map particles in physics in the standard model to the equivalent particles in programming, and then why they're useful and how they're useful, and pretty much why certain particles do certain things. So applications you don't really need to look at because that's just a sample code. Asymmetrical you don't really need to look at. I'm going to save that probably for another video. That contains code that runs, even though this is in Kotlin, and Kotlin runs on the Java virtual machine as well as the JavaScript virtual machine. There are a few things that are not identical in the way it does. For example, how you create an instance of a class in a browser is slightly different than the JVM. So I have kind of like asymmetrical code that is different. It does the same thing, has the same interface, but is implemented differently on different machines. So, since I'm not talking about the server right now, and in fact, that's not open source yet. So I'll save that for another discussion. So what we care about is the symmetrical code. And in here, if we look at, let me start with physics itself. Probably the best place to start is with the atom. Most of the things when you're building an application, you can think of an atom as synonymous with a field. If you have an address record, a name, address, city, state, zip, those things will extend atoms. The zip code is an atom, name field is an atom. So kind of gone are the days where you probably create a data object with strings in it. You'd have normally maybe name, address, city, state, zip. These are all strings. In this case, they would become atoms. And the name, you would, for the most part, add them into your dictionary. If we look at applications, this is very dictionary oriented development. I'm creating all my atoms. Here's address, and it extends atom, and I'm going to put whatever properties in here. There's some more superpowers coming, by the way, and I'll get to that. I'm working on many things at once, but you basically create a dictionary of particles of atoms, and then you want to create a composite like an address row that now contains each of these atoms. Let me go here. If you adhere to making every field an atom and then build atoms together into composites that become compounds or molecules, all the superpowers will work directly and you really don't have to do any extra work. Values that, if you see here, when this starts, I'll come back to why I'm using with. It's not really Kotlin. It's kind of a blend between Python, Java, Kotlin. I'm trying to program in the lowest common denominator between multiple languages so I can write a transpiler. Basically, the goal is that I'll develop in Kotlin and run it through transpiler and generate Python, but Python doesn't have multiple constructors, and Python and Kotlin allow for default values in functions, but Java doesn't. So I'm kind of bringing this down to the lowest common denominator. But you can think of with is the constructor. And, I have the empty constructor always constructs the mixins. kind of by convention. I'm using the init block to assign any values, which works fine in Kotlin. And then the with statement becomes the constructor that takes values. Normally in regular Kotlin, this would have the constructor keyword, and would take these values, but that's very hard to translate into Python. So with this constructor, it's adding name, address, city, state, zip to the compound. You can think of the compound of a list of atoms, where a molecule is also a list of atoms. Once you do that, if you access it by giving it offsets, like you take the name it's putting it in the last position, you keep upping. Actually, this 0, 1, I'm adding address is offset of 1, city is offset of 1, and it starts with wherever the last value is. This thing last is, going to be -1 because it's not adding anything. So then you can, when you do getters, you get the value based on its position in the list. So you can think of, you have a compound that has a lot of atoms. When you access it, you're going to get the address atom using this offset. Now, what it gives you by doing that, instead of creating fields, I don't even think I need this anymore. I think this is debugging code. Yep, let me take that out so it's not confusing. Add some debugging code. What this gives you is the atoms and molecules they have the ability to emit themselves. They can iterate, a molecule will iterate to its atoms, the atoms will go to the protons, and so on, and go all the way down and create the photon emission that can be absorbed. So if you take this approach, you don't have to do any extra work. You just basically have an address row, extend compound, add your atoms, and you're in business. So if you want to do the analogy,
can I just ask, just number one of the reasons, if you could maybe explain to folks why you're trying to write in like the lowest common denominator to kind of just, you were mentioning you want to reuse as much code as you have, because then you just condense the entire file set into something much smaller than a lot of things that we have out there, is my understanding.
Yeah, to maintain, in the past, I like, God, probably in physics, I had a version of it that ran on the Flash player, and a version that was written in Java. And I didn't have a transpiler to transpile between the two versions. So what I would do is I'd change a line of code in my Java version, and then I'd go to the ActionScript version and change it there. And I'd keep them I'd develop twice and test twice. And it was very time consuming. I decided I would never do that again. I chose Kotlin because Kotlin pretty much runs everywhere. You can run it in the browser, you can run it on the virtual machine. It works in Android, iOS, you name it. So I didn't have to deal with that problem anymore. But now that I'm coming back and working on a Python version, I'm back with the same problem, except I want to approach it differently. By taking programming in the lowest common denominator between the two languages, this becomes very easy to translate into Python, because this initial constructor, all that's going to be in it is set self. So that's more or less how it's going to look in Python. It's going to it's going to do whatever's in the initializer construction, generate the underscore init underscore, for those who know Python. It's going to generate that. And then it's going to create a separate function with these adds. And, there'll be some syntax translation that's going to have to go on. But the goal is that I write it in Kotlin, test it in Kotlin, press a button, regenerate all the Python code, and then just test the Python code to make sure nothing broke. I had some similar experience with this maybe about 5 or 6 years ago, where I was doing some Canvas graphics program in Dart, and Java FX implements the Canvas API, and Dart and Java are very similar languages. So I did write a transpiler for that. It was a little bit easier than going to Python. From Java to Dart is very close. But that worked out pretty well. Programming in the lowest common denominator of the two languages, I was able to transpile one language into the other. And since Java FX implemented the Canvas graphics API, it translated nicely into the web Canvas API under Dart. So this is going to be a little bit more, sophisticated and tricky because there's a lot of transformations I'm going to have to do between the two languages. But I'm basically setting up. I'm in the setup phase. I haven't began working on the transpiler. I'm trying to already get, like if you saw a lot of commits, anyone who looked at the commit log, there was a tremendous amount of changes in there where I didn't change any functionality. I just changed the way Kotlin is written. Once you're using the Kotlin library, you don't really have to adhere to these conventions for anything that you write yourself, because, whatever you write won't, more than likely, if you're programming in Kotlin, your target will be Kotlin, and you're not thinking about transpiling it. So you don't have to worry about it. It's just inside virtual physics, it's going to have some weird conventions that are not really Python, not really Kotlin. And, if I decide to do a Java version, not really Java either. So that's it's a work in progress, but that's the thought that goes into it. And, why you might see some weird conventions now that weren't there before, just, a few weeks ago.
Cool. And one other question: when you're storing like city, state, zip, and stuff like that in those atoms, is each one in its own instance of an atom, or how does that work?
Yeah, this basically, it creates an instance of an atom and adds it to the list, creates another instance of an address and adds it to the list. So this becomes a 0 element, the 1 element, 2 element, 3 element, and you get them back out. Last is -1 + 1, so name is 0, address is 1, and so on. So when I say get address, I'm getting, this would be position 1 and returning it as an address. And by convention, you don't want to reset these values. It's not that they're immutable, and that's a whole other subject when we get to functional programming. I'll save that for the end. When you build an atom, you want to update the values in the atom. They're not immutable, but you don't necessarily want to replace an address with another address. There's very little need to do that. So you don't need setters. It's usually these molecules and compounds are constructed the way they are. The individual atoms can go through state changes, but you're not really, in real life, you're not plucking out. If you have H2O, for example, you're not plucking out one hydrogen and popping in another hydrogen. It's pretty tightly bound. So, you want to think of this the same way as you would in chemistry. Like once a molecule is constructed, the state of that molecule can change. For example, you can boil water and its state will change or its temperature will go up, but the H2O will remain intact. So this is kind of the same idea. The goal is to follow physics and chemistry as closely as possible. And towards the end, you'll see some unfinished work, but a lot of superpowers are coming. And we can have kind of a philosophical debate as to why that is. I believe that the closer we get to the laws of physics, the more amazing things just seem to work out. Now, is it coincidental or not? Like everyone, can have opinion and debate that. I think that there's something about these patterns. So let me continue down. When we go to atom, let me go to the atom class. Because this is where most of the magic is going to be. When we look at atoms, they have orbitals, which is the outer orbit of an atom. You have all your electrons. The electrons, as you would expect in electronics, are used for creating things like diodes and conductors and capacitors and so on. We're really dealing at the electron level. And so that's what they're actually used for in here. When you see the sample code, We create, it's the beginning of rudimentary electronics. There's some amazing new superpowers that I can talk about later. We can start building transistors and switches and all kinds of other stuff and do it in a kind of electronics way. Like, the goal is that people who are electrical engineers and want to bring their knowledge of electronics into virtual physics and enhance this, there's room to do that. And in theory, it should work because this is following the laws of physics very closely. And I have some rudimentary stuff. I want to say this, although it's taken me over 20 years to get it to this point, of trashing it and starting over, trashing it and starting over. This is only version 1. We just got to the tip of the iceberg. I see this as now a proof of concept that we can use the laws of physics and the patterns in there. And it does bring superpowers for unknown reasons. It makes the code incredibly small, compact, and we can just do stuff that normally, like, if you want to, you'd have to use JSON and JSON parsers and, all this open source just to transmit strings. And this seems to handle it all by itself. There's so many superpowers that come with this. So if you think of the atom as a field, the values are now stored in the nucleons. And I also put some handy, if you want for more information, you can look up an atom. I put a link in Atom. It is kind of important to understand the physics and learn a little bit about that. Like when you follow the nucleons, let me actually give an example. Like, we can go to the nucleon, and unfortunately, I couldn't figure out a way, if anyone knows, that to make it clickable in IntelliJ. But let me take a tab and bring it down. It describes, what a nucleon is, and a nucleon can be either a proton or a neutron that is in the nucleus of the atom. It kind of helps to understand it. It actually, some overview, it describes a nucleon that's made of quarks, and we're going to get to that because when we get to the protons and neutrons, they will be made of quarks. So having an understanding of that becomes useful. You'll be able to see this whole project is an interpretation of the patterns. If you look at one of these particles, the real problem, let me go down to the proton level. It's when you look at a proton, where does that fit in programs? Where does gravity fit? How, the big problem was, how do I use this stuff for something meaningful? When should I use a neutron? When should I use a proton? What does a quark do? The list goes on, and I have a lot of particles here that you'll see empty classes for, that they're kind of placeholders. Some I know what they are. I just have to finish implementing. Some I have no idea, especially a lot of the antiparticles. A lot of them, some of them I know, some of them have no idea how they're going to fit, because I don't know where in a program certain antiparticles would actually exist and what do you do with them. But many of them I figured out, like, and that's what you're going to see when we go down into, let's say, a proton. Let me grab this here. And okay, a proton has 3 quarks. Without reading all of this, a proton is a type of baryon. Baryons are, you can think of them as quark containers with 3 quarks, which would be a neutron, or a proton is a type of baryon. So if we go to the proton, it extends baryon. If we go to the baryon, there's 2 types. There's 2 types of baryons. You have a neutron and a proton. A neutron has 1 up quark and 2 downs, and a proton has 1 down quark and 2 ups. So you'll kind of see that, if you read up on it, where is the value stored? The values are stored in the proton, in the quarks. And I won't talk about elements. We can have multiple protons. Protons can decay into neutrons, and when you add neutrons to an atom, it becomes heavier. And in a sense, neutrons are dead weight in that they don't interact. They don't change the chemical reactions. Hydrogen can have none, 1, 2. I'm not sure how many neutrons it goes up to, but it's still hydrogen, and it still can form bonds, and it still can be water. So what is a neutron used for? When I'm using in the neutron, I'm storing the prior values. This gives you the ability to roll back. You take on more dead weight, the proton decays into neutron, the atom gets heavier, and at some point you can decay it the other direction and restore the proton, and the neutron basically gets ejected. And so it adds dead weight, but that's the placeholder for the neutrons. When you look at the up quark, here you have a down quark. This is actually where the value is stored, not implemented yet, but this is where a new superpower is coming, is in the other quarks. It's going to store, there's really a triad. If you think of every field, it has its value, it has its format, because, a date, if it's just an integer in milliseconds, it doesn't look like a date and it's meaningless. You might want to store the value, like epoch time, as some, gigantic number based, I think, off of January 1st, 1970, but that's not how you want to see it. So it has the format and it has constraints. And coincidentally, we have 3 quarks to work with. That just is, there's a lot of amazing things as it comes out. It's like the standard model becomes an amazingly well thought out computer in itself. So I'm working on that piece right now to add it, and we're going to have constraints, format, and value in every field. Every atom has a proton. So every value has those 3 components. So you can kind of think of those as the most fundamental pieces that make up a proton, is value, format, and constraints. You can't have a date with 5-digit year, at least not yet, not in today's date. Everything has constraints. You can't have a zip code 000 or 9999. It has constraints. So
physics has constraints. I mean, we got the Planck units. I mean, those seem to be pretty fundamental constraints of our reality.
Absolutely. And it seems like when the proton was built, these patterns are kind of there. They were giving us a clue that a proton is a value, because it has a charge and it does interact with other elements and atoms and creates things and binds, and neutrons again are dead weight, but they're very useful. But there was a secret in there. Like, why is there 3 things as elemental particles? Like, why are they inside the proton? What do they do? And in hindsight, it took a lot of thinking, a lot of doing it wrong, until it made me realize it's like, well, when I think of a value, what are the 3 most primitive things you have about a value? And it's like, well, it's the value itself, the format, and its constraints. Without those 3, it's really not a value. Like, a zip code is not a zip code if it's all zeros. And a zip code isn't a zip code if it can't be formatted in 5 digits, at least in the US. In other countries, there'll be different constraints, which is fine. So now there's also interaction with the gluons, and I'm still working on that. That's coming probably after this next iteration, probably a couple of months down. I don't know how I'm going to prioritize whether it'll be the Python version. There's really a lot of work to be done here, but without promising to any particular order that I'm going to do it, that's coming with the gluons. And so now when we get into this, as we look for more like a new element, we have hydrogen. Let me go into the code back. So we have a proton, and for the most part, all this is working with it's only working with hydrogen. I haven't created helium and the other atoms. Where do these elements come together? And what it does is a helium we know has 2 protons. So how is that useful in physics? How is that useful in programming? Like where have I seen helium before? Like
Well, according to Let's Invent That, thank you for joining, my friend. According to them, they're saying that they see geometry, order, and dimension.
Yes. Geometry, order, they're all there. And actually, as we go down into this, you'll see more of it. In fact, the dimensions right now, there are 5 dimensions that I'm using, which is time, space, mass, charge, and temperature. And there's also 3 other values. All particles have spin, they have angular momentum, and there's one other thing I'm using in there. Spin, angular, and momentum. Let me go look that up. I'm drawing a blank.
I remember this too. We talked about it. I totally blanking on it.
The wavelength. That's where all the values are actually stored.
Yeah.
Right. So now we have 8 things. What space is used for, programs do have geometry, just like was mentioned in the chat. The programs get bound together where things point to other things. For example, the zip code is not meaningful unless it's contained inside of an address record specific. And the zip code can be pointing to the molecule that contains it, or it could be pointing to some other record that it belongs to. But eventually, if you look at a program, there's pointers all over the place, and it becomes multi-dimensional, like things are pointing. So space is
maybe a little something like some of these little diagrams we had here. I'm just bringing up some of the little maps you sent me.
Right. These do become useful, and you can see that we do have space. Charge and mass pretty much define a particle. Right now I'm using its class ID, but those are reserved. If we know the charge and we know the mass, we can know that this is a quark, an electron, a tau. Like each one of them are unique. Time, all things have time. So those are primitives. What temperature is a value. All particles have, can store state, and there's some value. In this case, temperature has a huge range. When we're dealing with numbers, financial numbers, we're not going to go to infinity, for the most part. We have constraints. So the temperature bounds is where, and wavelength is where values are stored. So to get an idea there, just so you know, at the most fundamental levels, when you go to a quark, it extends particle. So let me go down. You saw the protons are made of quarks. And if we go to quarks, they extend particle. And I'm working on the gluons. The color charge is what holds the quarks together. And where this is going is the color charge is a continuous validation. They fire in a certain order, and they're constantly changing colors. And this, after thinking about it for a long time, in addition, you can have constraints and you can have format and you can have value, but it's meaningless unless something can act on it, unless something can validate the constraint and say that this fails the constraint and set the quark color. So this is where the gluons magically just seem to fit, because they're constantly, you can almost see it as like a cleanup action. They're constantly running through the quarks and making changes to it. And if you think about programming, it's like, wow, well, having a constraint by itself is not enough. Just having these quarks sitting there, something's got to keep running through it to make sure it stays consistent, to make sure the constraints are there, and we have something that can be formatted. A bogus date, ABCJ can't be formatted as a date. So that's what the gluons and the color charges are going to be added in to do. But within the gluon, it now extends particle. And within the particle, we have time, charge, space, mass, temperature, wavelength, spin, and angular momentum. And pretty much spin is kind of useful for setting flags. Like we have, spin of 0, 1, or -1. Wavelength is pretty much infinite value. Could be anything. If you think of a string, it's just some giant number underneath all that. The same with temperature. So everything ultimately boils down to particles, and particles have a lot in common, all of them. So this makes it very easy to transmit and emit, because unlike regular programming, when you're building it out of just stuff, random stuff, I get a library, I download it, if I wanted to make a general purpose emitter for this particle, for this thing, I don't know how to do it because I don't know what it is and what it's made of. But now with virtual physics, we know everything is made of atoms and everything has quarks and all the way down. So now we can have a general purpose emitter. It knows how to emit these things. All fields are made of atoms. Atoms are put together into molecules. So we can build very interesting things. We can create an application-specific address record, but virtual physics knows how to serialize itself and transmit itself and reconstruct it. As long as the added components, you can think of it, if you have a blueprint and you want to build a house, you do need all the 2x4s there. And if you made some custom 2x4s, chemistry didn't just create these 2x4s, somebody cut it. So you need to create, the address record, which acts as a template, and you basically add it to your initializer for the absorber to recognize. But once you've done that, there's not much else to do other than define it, because your address row is made up of a compound of atoms that the emitter knows how to handle. So everything is transmittable everywhere. And what makes it even more incredible is that we can transmit, as long as we have the same components on both sides, we can actually transmit from Kotlin to Python, and it will reconstruct it the exact same way. It's language independent, as long as they both implement virtual physics in this, the same library in the same way. So what we're saying is that everything in the universe is compatible as long as it's made following the same rules, which is how everything works. That's how come metal works with metal and melts at the temperature, no matter where you are on Earth, no matter how you're doing it. Aluminum melts at a certain temperature. And, we're basically creating a programming library that's fundamental. And it's even fundamental to all languages. It goes below that. The language, normally we tend to think of the language at the bottom. We build up from the language and build the library. But in this case, it's a little bit inverted. We're saying that I'm only using the features in the language that support this library. The library is the most core, and then the language gets wrapped around it. Right now, I'm using the lowest common denominator, but the language is actually less fundamental than the library. The virtual physics is core, and everything has to be built on that.
Well, that almost sounds like engineering right there, Echelon.
Absolutely. I believe this is the beginning of true. We call ourselves software engineers, but we're not. Like, chemical engineers are governed by the laws of physics, mechanical engineers, nuclear engineer, everyone's governed by the laws of physics except us. Well, hopefully this changes that now, because we're going to have the same constraints. We can debate on whether I interpreted the patterns correctly. And, some of it could be a philosophical debate. Somebody can come up with a better, closer interpretation, which would be great. Is there a better way to put atoms together? We're kind of governed by the laws of physics. I've noticed that the closer this gets bound to all the particles, the harder it becomes to violate the laws of physics. But the goal is true software engineering. If somebody has a chemical engineering background, reads this library, they're bringing a tremendous amount of understanding with them, and now they can begin to work with it using the concepts that they already know.
See, that's one of the big things right there, because I postulate that, especially since we've got a pretty decent understanding, but there's still lots that we don't know about. Like the atom itself, it's like, all right, it's got these quarks, they're cycling, there's these gluons. It's like, does anyone really know what's going on? I don't think so. But I think we can actually get clues from this, and that, especially if you or somebody else out there that wants to contribute to this can find a way that increases the efficiency, and it seems to persist without creating all new laws of physics per se, we could probably actually use that as a hint for physics itself, I claim.
Yes, there are some cases where I have tried to work backwards because it seems like there's one way we predominantly look at the laws of physics. We look at it from a mathematical point of view. But there is another point of view. There's information point of view. What information are all these particles carrying? And from a proton, we know there's 3 quarks. So it's carrying 3 pieces of information, no more, no less. Why? Why is it 3? If you start looking at all this and you start decomposing it, you start looking at from information points. Well, it has angular momentum, there's wavelength, there's certain things that all particles carry. Most of them have almost identical. All particles do have those properties. And other particles are made of subatomic particles. They build together. You can look at it mathematically, but you can also say, like, what information is this adding? And why are there only 3 quarks? And does that mean something to me as a programmer? What are the clues? And it took me a long time. What is fundamental about a piece of data? What is it? And it took a long time. They're like, well, it's constraint, format, and value. There's nothing more fundamental than that. If you don't have those 3, it's not really a value. But there's a lot of other properties that data can take on. So finding what is the most fundamental is not always obvious. And this is where some of the superpowers are going to come with the next iteration, where I'm going to support elements. We're going to have hydrogen and helium. So what is helium? Helium becomes a new kind of, the elements become a new kind of interface. Coincidentally, again, as I use the patterns of nature, new superpowers, interfaces become not enough. An interface gives you a signature saying that this, an atom has a get proton function. It has these different interfaces that we can use. But when you group atoms together, how do you say in an interface that this atom must have 2 protons? This atom must have 3 protons. And interface is not going to help you with that. You can do validation. But now if you have a helium, and a helium can only be constructed with 2 atoms, it serves as a kind of interface. So why would you want 2 protons? This helium atom takes 2 protons. But why would I want to mandate 2 protons? What superpower does that give me to have more protons? I already have the value. I have format. I have constraints. I'm good to go. Like, I can do everything with that. Well, we now have a new superpower. Imagine the second proton has the field name, address. Your name atom is helium. It has the value and it has the field name called name. The second address has the value, the first proton. The second proton has the word address for its field name. So you transmit this helium over the internet to a browser who reads these atoms, these helium atoms, and dynamically generates a form and puts the value in the field and puts the field name right next to it. And because it's a kind of interface, it says, I must take a list of helium atoms. I can now dynamically build a form with the valid names. So now atoms can now contain their own metadata. They become self-describing. And each of the protons add a new property. So we can have the color. The zip code is always going to be presented red. Everything else will be presented blue. So we can basically transmit that kind of information. Or access level. 0 means, it's transmitted, but this particular user has no visibility to it. 1 means they can read it. 2 means they can edit it. A form builder can now build dynamically. We can take these values and put it in the dictionary. So now we can set constraints. When they type in the zip code field, they don't get more than 5 characters because that's a constraint on the zip code. And with the gluons firing off, it'll validate that and give you the correct message. You'll put the field name there. You'll put the color, whatever properties you want. You create new elements. and you have a kind of interface because the form builder is expecting helium or lithium or, however many protons it's expecting. Now you can create self-defining atoms that define themselves, including their validation. Everything goes with it. And if you take the dictionary approach to building, you create this address, and what's coming is the ability to add these different properties. There's going to be a core set in the base of physics itself, like field name, axis level, probably alias name, certain things that we're all as a community going to reuse all the time. We'll have different value protons, but each application can now create their own and add it to the dictionary of protons. And when you construct an atom, not only will you say that this takes 3 protons, you can say these are the protons that it takes. It takes a field name, an axis level, and whatever else you want to add into it. So it becomes a new element. And then you can guarantee the construction of it by defining helium or carbon or oxygen, however many protons it should have. And that becomes its own kind of interface at a new level of abstraction. Now we're going up from the language level. We start at the library level, then we go to the language level. Now we're going back up to the library level of abstraction. So now we're doing chemistry. And we can do some very interesting things with that now. Now we're thinking at the chemistry level.
Right. And we know a lot about chemistry and stuff like that. That's a level like where we seem to be able to start to understand. We're coming out with these new compounds and polymers and everything like that. And what it kind of sounds like, it's almost crazy in a way, in that a lot of times when you think about programming, it's like, okay, we've got the binary stuff, and it's like, okay, we got the Kotlin language because it can do these great things. It's translatable to all these areas. But it literally reminds me of a story that I heard Professor Wolfram say at one point, where I think it was it one of the ancient Greeks, maybe Autonomous or something like that, where they had the concept of like, well, what if the building blocks of reality was kind of like making a sentence where it's like you're taking your noun, this, you're putting these things. And a lot of folks were like, well, that kind of makes sense. And then a little later, people are like, oh, that doesn't make any sense at all. Fast forward a couple of thousand years, and even Wolfram the other day, he's like, oh, he actually may have been more correct than what people are thinking, because that's what I'm kind of seeing here. It's like you're taking maybe not quite full natural language, but more or less the language of like physical reality as we know it, and using that as the parameters to construct a new form of reality, a new kind of programming, if you will. Did I butcher that? Am I
No,
okay?
I think it's right on, because this is a philosophical debate. This has superpowers that I don't know of any library that has these capabilities, that you can wire them together in diodes. You'll be able to build transistors out of it following the patterns. You can emit this stuff without using JSON or XML, and it'll completely absorb it. It'll emit between languages, and you'll get the exact same structure back, with one line of code to emit and one line of code to absorb. Like, I don't know of anything that has that capability. You can build together monomers. Like an address record is a kind of monomer, which is, a polymer is like row. You can think of it as rows of data, rows of monomers, and then you apply a catalyst to it, and you can break it apart and select. It just seems so powerful, and it keeps happening. This is a thing that I noticed. The closer and more authentic I got to the patterns in physics, the more powerful things would be. All the times that it didn't work was when I invented something, when I thought I was better than the laws of physics and had a better idea. Those were always the things that screwed up. I'd build on top of it, thinking like I did it, and then it would start crushing under its own weight. And it was because I invented some of my own particles to be smarter than nature. And, now I'm not doing that. If you look, what's here, if you look in the particles, let me go into my absorber. Let's go to atoms. Some of these are empty as placeholders. But if you start looking, these things extend, and I'm probably going to rename this. Actually, this is even bad. Let me go where my entire particle list is. Actually, the best way to do it is just run it. Let me put a breakpoint. Actually, if I just run this, it'll spit it all
What
out.
happens?
It's compiling. One of the secrets for being able to admit this is every value that you see has a unique class ID in base 52 to make it really compact. And, probably in another discussion, I'll talk why I didn't use base 64 and I created my own base 52. So it's the letters from lowercase a to z, uppercase a to z. It's very compact, and these are the class IDs. But if you look in there, outside of user specific stuff, like a key value you can think is application level, that extends a diatomic atom. Like it's a molecule that has two atoms. It's a diatomic. Let me go to that so you can see how that's made, just to give an idea. Because in the real world,
I'm just amazed looking at that base 52. I can actually understand what that's saying. Okay, BA would be a key value, BB would be a metal, blah 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 blah. I'm like, that seems pretty condensed.
It's with 2 digits, I can basically reconstruct. I look up in the list, BA, it's key value, and I create a new instance of key value. Then I have the emission string that is following. I know that this is a molecule, so it's a list of my atoms. I know that I have an atom, which is a list of nucleons, and each type of nucleon, it has its class ID, which is this. So I can construct, a mass, space, temperature, and then it has the length of the string that to set the field. So it basically reconstructs itself. This is only possible because I know I'm using virtual physics. I know exactly what I'm dealing with. There are no things that don't belong in the universe. Everything is a material or something that I'm making out of these materials. So this way it's self-propagating. It can transmit from machine to machine. It can transmit in any language as long as it's using the same virtual physics. That it's critical that we have the same library in every language everywhere, and then all these languages can communicate with each other without any infrastructure, without any open source that we got to download. They'll just communicate with each other. And here when you look at the list, I didn't invent anything. These are all quarks and kaons and downs, and not
those are things that I've heard within physics for a long time there. I mean, it's just even conceptually, it's like I feel like maybe I'm the only one that feels this. Maybe other folks share this, but I feel like this seems like such a great idea. Surely somebody must have tried this. And I feel like, according to some of the deep, and again, I know we've had some of these discussions, because when I found out during one of the Wolfram live streams, it's like, oh, we go down to like the atom level and stuff. And it's like, well, we had to maintain this coherent language for 35 years. So occasionally, well, there's a hack here or there's a hack here because, well, he's been running a business for 35 years. You can't just be like, oh, we're going to shut down the entire product line and stuff. So I feel like folks have tried this, but I feel like often when you're running the business, you have to keep going. You can't just spend all that time and energy trying to figure out. But that's what I think you've spent the past 20 years and just continually gone back to it, because it's like it seems to keep improving. So I just want to comment on what Nuno was saying here, because I see him with the Wolfram chats a lot. Basically, they're saying that they're a lay person, blah, blah, blah. But people like to think about these things. It's like, no, I was in those same chats with you. It's like, I was still amazed. I just happened to be blessed enough in my life where it's like, I'm like, all right, let me do some things here, see what's going on. And now I'm here. And it's almost unbelievable. And then I just want to touch upon Let's Invent That's comment. They're saying that this could greatly reduce electrical power consumption in data centers, given its low density, need for memory, and increased efficiency. So any thoughts, comments on that?
Actually, I think that's true. The server is 1.1 megabytes. it's so small and so fast, and it's a real-time socket server. I'm not doing the request and response thing. And part of the reason is I'm working on yet another project with this for remote drawing. I don't know what order all this. There's so many projects. Having more people involved would definitely help. But the idea is that on the server, you'll be programming, and if you want to draw a box or you want to draw on the browser, you would basically program as if you're programming only on the server. You'll forget there's a browser. And then as you set these values, because we can have diodes and values can now transmit themselves, from machine to machine using emissions. And with the diodes, we can have, when you create one atom, like one of the things I'm have is a remote atom, it'll automatically draw on the screen. So gone will be the days when you have to deal with all this extra infrastructure. The idea is that, it's an experiment, but we can basically program on the server and just assume there's a real-time socket talking to the browser, and whatever I draw on my virtual environment will just be happening on the screen, and all messages like keys and mouse movements will be transmitted back and will come into the server as if they happened locally. And this server, granted, all the features are not there, but it's 1.1 megabyte. And to test the performance of it, I did a denial of service attack on myself. I opened 10 tabs of Chrome and 10 tabs of Safari and put a program in a loop. And all it did was attack my server, which is running on the same machine. So I'm not even dealing with network delays. It's 10 browsers running full speed, pounding on my server, and the server.
I didn't know it was. I didn't know it was 10 tabs. I just thought it was just the 2 browsers. Okay, that's more impressive.
It was 10 tabs times 2, so it was 20 tabs pounding on my server. I let it run all night, and it was bored. The server was just like.
So wait, hold on. So what you're saying is you locally DDoS attacked your own server, and it was like, meh.
Yeah, it handled all the requests and didn't crash. Now, there was no load, like it wasn't doing a database lookup for all that. Like, as the load goes up, if it's doing a lot of queries, but the point is the server itself, if we're doing some heavy duty, million line calculation, it's going to take a million lines of calculation, but the server adds almost nothing. It's so fast. Now, one of the things that, people look at this and say, well, I can have a zip code that's just a string. That's really tiny. You have an atom that has protons, quarks, all this metadata, and so on and so on. So surely that must be heavier than using a string. So how could this possibly be faster when you have something that's so complex? Well, what it seems, and I don't have an answer because it does seem like, this can't possibly be fast. This has to be slow as molasses. So why does it seem to work? Well, what ends up happening, I believe, if you just have a string, that only tells half the story. Then somewhere else you have zip code validation code that validates the zip code. And then somewhere else you have converting this to JSON and transmitting it somewhere in this big string. And somewhere else you have code that takes the JSON, parses it, constructs all these new objects. So we're looking at it, say, oh, well, here's just a string and you have an atom. And it's like, well, you don't have just a string. You have more than an atom's worth of code that from the time this goes to the screen and goes to the server and goes to the database, you executed 1 million lines of code. So compared to that, my little atom is actually very fast because everything you ever want to do, it's metadata, it's transmission, it's validation, you name it, is in these small set of particles. So the reason it looks like it's so big, but actually executes so fast is because the whole library is so tiny. It uses very little memory and it reuses everything in the most efficient possible way. And now that's a philosophical debate, that is it the most efficient? I'm saying that the laws of physics and the patterns in nature somehow are optimized better than we can ever do. And Am I right? I don't know. It's a debate that we can have. Is this all coincidental that this tiny amount of code that's using such little memory can do all these things? I think it's because of physics. And I noticed the thing that kept me going, and sometimes it was almost embarrassing because I'd run into somebody I hadn't seen in 10 years, and they'd be like, you were working on some physics thing. How did that ever turn out? And it's like, oh yeah, that was 10 years ago. I'm still working on it. I haven't figured it out yet. But the thing that kept me going is remarkably, the closer I got to the laws of physics, the more superpowers kept coming out. And it's like, man, like I quit many times. I said, I just can't do this. And like, I'm wasting my life. It's never going to happen. But then, after a week or two of quitting, I'd be like, man, but some of these things just seem to work. And then next thing I got to do a new version. I just did it wrong. And, as I mentioned in one of the other videos, that I think the thing that made this become successful is I learned to ignore myself. I learned, don't have any ideas, just interpret. If I don't understand what are quarks for, just interpret it, figure it out. It must mean something. It must mean something. Don't be creative. Don't make smart protons. Just protons have 3 quarks, deal with it. No more. That's all you got. And there's an up and 2 downs, or a down and 2 ups, and whether you're dealing with the proton or the neutron, deal with it. And
You
it
have your
must mean,
constraints.
those are my constraints. And real engineers have those constraints too. Like an electrical engineer may be able to say, damn, if I can make the proton negative, I can build a remote control with only 4 transistors and half the price. But they got to deal with it. This is the way physics works. So
I know. Just imagine the most effective form of modeling reality is using reality itself.
is
It's a
using
guide.
reality itself.
So that's what I'm getting from Let's Invent That. And oh, awesome one. Oh, that's a fellow something debate there. Following God's creation to make a VR creation. Ooh, I'll leave that there.
I think this is going to change things. It's going to need a lot of thought. It's going to need people who really understand electronics I believe we can actually build circuits using this and build simulators using it, as long as we understand electronics. Then we can use that. Was the whole goal, to get this version 1 out. When I finally just started interpreting, I'm not sure if all my interpretations are best, and some things I don't know what to do. Like, we have a strange quark. I'm not sure what to do with that right now. Right now it's empty. Like, where does a strange quark exist in programming? I don't know. But more people thinking about this. If somebody's wants ideas for their PhD, I mean, you're supposed to be doing original work, and there's a lot of opportunity here to do a thesis and come up with ideas on, how electronics relates into virtual physics, and how does chemistry, how do we do binds, how do we do catalysts? Like this, there's so much room for new original work, and even philosophical debates as to, what is the correct interpretation and what could be a better interpretation. I'm not claiming I got it right. I'm just claiming I got enough to lay the groundwork that we need to now think about it. I think this is opening up software engineering, where the word really means engineering. And we now have peers, our chemical engineer friends, our engineers, and we can call ourselves engineers now. And they can take their knowledge that they learned dealing with real physics and real chemistry, and start to learn to program and find all the mappings, and even find flaws in this, because they're chemical engineers, because they're electrical engineers. I think that's remarkable. I think that, everyone here, you're seeing the beginning of what I think is going to be the next phase in computer programming, and where true software engineering begins. I think this is the beginning. And there's plenty of room for debate. I'm open to hear other sides. As a matter of fact, Matthew's hosting the Physics Monastery website, and anyone who has interesting work and wants to contribute, Matthew, you can talk about that for a sec.
Yeah, yeah. No, let me know, because one of the things that we're trying to do at the physics monastery, because like we have a lot of folks, they'll see like Thad's work, they'll see your work and everything, and those, to be fair, those are like the two major projects we have going. It was also, I'm looking there, I'm like, I kind of came for the physics, and I learned about this. I'm like, well, both these ideas, again, if half of what we are claiming is true, I believe individually each of these ideas are revolutionary. Now, I'm hoping it's more than that, but even that, the sheer fact that we have those projects going on, the ability to step forward into perhaps true software engineering, to be able to build programs to help increase the efficiency. And for me as a gamer personally, if you can have a live socket server update there, you basically make like server bound processing in video games. Basically, that whole Google Stadia fiasco where like, we'll do all the processing on the servers. And then they realized that was an incredibly hard problem. And in actuality, it kind of tanked. But if we have this efficiency, if we can literally use something where it's now, I think, only like 375 files, like a 1 megabyte base bare bones server, and then you build on that, we might actually be able to do it possible. Long story short, we could probably have a lot better video games, if not literally be able to start engineering things where we're starting to push the levels of potentially Star Trek level technology, where it's like, oh, we're not just stuck on Earth. We might actually be able to go out there and explore the cosmos and stuff. But one of the things what we want to do is, the only reason I'm here is because of the power of the internet. It's literally as much of a dumpster fire as Twitter is. That was how I met Thad. And through that, I happened to meet you and other folks. And I truly believe that there are a lot of folks out there that have a lot of good ideas. And I think the physics monastery is a place for people to come and think, have discussion, to have passionate but constructive debate about things, and be able to share their ideas and get them out there and everything. Because I know I've had different folks on and interview them. And as we're getting this more and more established and everything, it's like, if you have a great idea, if you have something that's important, reach out to me. Send us an email. I'm still getting the website all together and everything. But as we're doing this, whether it's on Twitter, whether it's here, whether it's in the comment section or anything, if I don't immediately respond, just send me another message. Don't spam me too much, otherwise those are one of the things that's spam and flame boards. We understand there's a place for that. Just if people are busy, just let them know. And if we can host you, have a talk, hey, that's how I learn things too. So we're looking for a place for folks to come together, share ideas, and help level up humanity. I know it's corny, but hey, it's true.
It is true. And I think that, people are really interested. There's a lot of different ways you can view this work. You can view it that you just want to use it and write an app with it, which is fine because, your experience with it, good or bad, released to the community so that we can fix things, make it better, is great. You can look at it from a philosophical point of view and write papers and, pro or con, whatever, just release your information. Or you can work with it. If you're a chemical engineer, like this is very skewed towards physics because that's what I'm better at. My chemistry is kind of weak. My electronics is kind of weak. You're going to find a million people who are better than me, who, if you learn programming and take your knowledge and bring it and inject it in here, we need that. So if you can write papers and think, the most important thing is learning this and, seeing the vision of what this could be and contributing to it in any way, whether it's building things. One of the ideas that I've had, like when I was talking about, helium and hydrogen, right now, when we're in IntelliJ, I can say file new, and then I can create, a new, well, maybe not go there, new, I want to create a Kotlin file. Right? And then within that, it's a class or an interface or an annotation. These are very language specific things. Well, imagine if we had a plugin where I can create a new atom or create a new molecule, create new helium. And then the IDE guarantees that we're using 2 protons. We said create new helium, and it actually asks you to specify the protons that you want to use. Now we're programming on a whole new level. Now we're bringing engineering to the IDE. Now this is an engineering tool, but we're building software out of it. I think the idea of that is incredible. And if anyone wants to think about that, pick that up, create their own project, create plugins for this that are just on a new level, the opportunity, I think, is endless for people to think about and contribute, because this is brand new. Like, this is, to the best of my knowledge, it's never been tried before. I don't know why, after the fact, after struggling with it for so long, it seems so obvious to me now. Like, why did this take over 20 years to figure out? It's like, duh.
Wait, well, okay, well, pause for just, okay, just take the statement that you just had. It's like, and again, I kind of said, it's like, well, surely somebody must have tried this. And then you think about it, it's like, well, how would you actually go about this? It's like, to do it and get it to a point, and then you develop it further, and then it kind of crumbles. It's like, well, then you're just building hacks on it anyway. And that seems to kind of be, well, what a lot of kind of software engineering, according to some people, might say, is a series of hacks anyway. So it's like, to do that, to do it well, number one, you'd probably have to have experienced programming from multiple levels. Basically, like, not just programming as it is now, not just programming as it was in the 90s, but maybe almost like you'd work with maybe some machine interface. So you would need to have all that exposure. You would need to constantly be working with all these different systems to see all the potential intricacies. And as you build it and you continue to run those different problems, not just have your boss yell at you, be like, just get it done by Friday. And it's like, I feel like spending that time, of course, it would probably take decades to try to get something like that.
And truthfully, I've been programming almost 50 years. And I, at every era, like in like the late 70s, early 80s, some shiny new thing would come out, and this is the way to do it. This is the latest, greatest. And we would learn that. And I drank the Kool-Aid too. This is the way to do it. And then I noticed, like 5 to 7 years, like, oh, nobody does that anymore. We have a new language, better way. And this is the new shiny thing. And then, 7, 8 years later, like, everyone forgot that. And, this keeps happening until after a while, I started getting like, all this is bullshit. Like, we're not getting anywhere. Like, there's got to be a better way. And I was always interested in designing libraries and frameworks, but none of mine ever worked either. It was, my version 1 was always seemingly the best, and version 2 got a little worse. And it's kind of it's like building a Lego set. When somebody wants to build a like what do you call a castle, and you have a perfect Lego set for them, and they can build the castle, they can build the walls, they can build the bridge, they can build anything with your Lego set. You're a hero in version 1. Version 2, somebody wants your library and they want to build a boat. Now you have a perfect Lego set with a rope, a rudder, a sail. And it's not so bad, but you have these exceptions. Version 3, somebody wants to build a car, and you have a perfect Lego set with a rope, a rudder, a sail, a windshield, a tire, and eventually you have a junk heap. It's not a Lego set anymore. And that's what always happened with my work and with every other library and framework out there. We just can't seem to get it right because the Legos that we're using are not universal. We can't build, sails out of Legos. So that's what kind of led me to thinking of the laws of physics. We have a Lego set, the protons, neutrons, electrons, gravity. We can build everything in the universe with that. And, why don't we just use that as the Lego set? And so it was really a lot of the failures throughout my entire career of never being able to build a library or framework that lasted, and never seen one that lasted. This by definition, if this is correct, this will last 100 years because it's physics. If the idea that we can build software using the same constraints in physics is true, then this is the library, and it'll get better, but we're not going to throw it out. Like, this is we've gotten to the point where we now have a base library that software will be the underpinnings of all software, and we've achieved true software engineering now. We're at the same level as the other engineers. They're now our friends. And to me, that's really exciting. And everyone's invited.
That's a very bold claim, Echelon. But the wise man once said, "Make it so."
Yes. So this is kind of my pitch. Like, I found this exciting enough to work 22 years on it. I think my claim to fame is that I'm patient as hell, like to the point of lunacy,
Well, sometimes the loons come out on top because let's bet that saying that if there was an equivalent of the Nobel Prize for software development, Echelon would win it.
Thank you. It's
so we got some confidence there. It's no, and apparently for something with very little advertising and an individual that posted their first thing on GitHub, it's been getting some interaction. I'm seeing there more stars appearing and stuff like that, and
I think
you're getting traction.
People are getting into. I think the Python version is important. It'll reach more people than the Kotlin version. But I think even in Kotlin, like the ideas, understanding the concepts without even using the library is important. Understand it is something that's really important. Because
is there anything else you want to touch? Is there anything else you want to touch on, or just kind of like get folks' thoughts, or what are you thinking?
Yeah, I don't know who's out there. If there's any thoughts out there, I pretty much.
Oh, I was asking you if you had any, if you wanted to go over anything else for particles right now, or kind of pause and just kind of give your final thoughts personally on what's going on.
Yeah, I want maybe a quick discussion of projects that are like the road ahead.
Okay.
Definitely the Python version. I have to write a transpiler on, anyone who did clone the project will see still changes, probably not as much as before, in the way the code is written without adding new features. I'm definitely going to be adding the elements very soon so that we can have self-defining atoms. That's a very important thing, that it's 90% there just by the nature that I already have atoms and protons. It's kind of remarkable that it turns into its own superpower just because it's there. So that's coming really soon. Longer term, I'm thinking maybe a Java version. I don't know if anyone cares about that, or if Python would be enough, but a Java version would, if I can get the Python version working right, then generating a Java one would probably be a minor step because it's closer to Kotlin. The server, I don't know if anyone's interested in that, but definitely the real-time socket server. I can think of a lot of uses for that. Remote graphic drawing is probably realistically maybe a year out. It may sound like a long time, but after 22 years of working on this, what's another year? And then whatever ideas other people come up with. This needs a database. I was talking to somebody who's interested in building a B-tree database for this. That would be a great addition. It would be a separate project. We can use writing a new database using virtual physics allows us new capabilities. We can use circuits to get notified when records change and things. It really is a whole new level. So those are the things that are coming. That's about it. It's all I can think of off the top of my head right now.
Cool. And those of you interested at joining, we got Echelon's GitHub. It's linked in the doobly-doo below. Throwing it in the live chat right now for anybody that wants to go check it out, download it, set it up, and then I think we got a conference coming up at some point in February. It's the plan. I believe we're doing, what is it? The third week. I think it's the 20. Bring it up. It's 23rd. I'm bringing up my phone. It's like the 23rd to. Oh God, terrible person. Okay, I think it's the 18th through 24th. Okay, so that's the third full week in February we got coming up. As we got a bunch of folks from the monastery, we're going to be going down in April to the Demystify Science folks conference down in Austin there for the solar eclipse and everything. Thad's giving a talk. I'm still seeing if I can get you more than just a poster spot there. I'm working at. I don't quote me yet, but Echelon may be giving a full formal talk. If not, they'll be going kind of like a little pitch thing. I'm going to be doing a little pitch thing too. So that should be fun. Still working on the website, but otherwise, you got links down below. Feel free to check out the GitHub if that's your forte. And other than that, take care of yourselves, everybody. It's a crazy world out there, but trying to let folks know there's still some good stuff out there. So take care, everyone.